Ryan, and today I'm going to be talking a little bit about some of the geological processes that were happening after Noah and his family stepped off the ark. And I think this period of time after the flood is really interesting, and it doesn't really get a whole lot of discussion in young Earth creationist circles. We spend most of our time talking about the flood, which, makes sense. It does take up a good 4 chapters of the book of Genesis. So it makes sense that we would emphasize that. And then we tend to skip over to the calling of Abraham. And there are a few events described between the ending of the flood and the call of Abraham, but they're very brief. Things like the Tower of Babel and the dispersion of people groups. Other than that, this period of time really isn't talked about all that much in the text of Scripture. So we're missing several hundred years at least of events that were happening between the flood and Abraham's time. But to account for this gap in the scriptural record, we can turn to the geological record. We can use Scripture as our starting point, giving us information on events that happened, like the flood, and then use that to piece together from the geological evidence what was happening on this planet as it was recovering from this worldwide catastrophic event. Oops, there we go. So before we get into exactly what was going on after the flood, I think it's important for us to kind of step back and put ourselves back into the flood and kind of realign our minds and really understand what processes were happening during the flood, because these will actually play a part in our discussions later on in this talk on what was going on afterward. And I think Genesis 7:11 sums it up pretty well. In the 600th year of Noah's life, in the 2nd month, on the 17th day of the month, on that day, all the fountains of the great deep burst forth, and the windows of heaven were opened. And you can read the rest of the flood narrative to get a better understanding of the flood in general. We can add up the timestamps that are provided and conclude that the flood lasted almost a year. Noah and his family and the animals were in the ark for almost a year. This wasn't just a 40-day, 40-night event with rain and water sloshing around. No. This was a long-lasting event, and it's one of geological significance. I especially want to draw attention to this term here, the fountains of the great deep bursting forth. What exactly does that mean? Well, there is much discussion to be had amongst Hebrew scholars and other Bible experts as to exactly what's being described here. But at the very least, it seems to be talking about some type of deep sea crustal movements that are causing the waters of the pre-flood ocean to literally overflow onto the continents, completely submerging even the tallest mountains of that time. This was clearly an event unlike any experienced before or since. And I would argue the best evidence left behind by the flood, or at least the most obvious evidence, is the fossil-bearing sedimentary record we find around the world. All over the planet, we find thick deposits of sedimentary rock layers that appear to have been laid down by water. They are filled with marine fossils, which would suggest that these are marine waters that were launched onto the continents, flooding them, which is exactly what we would expect to see from Noah's flood, since this was a worldwide event. And we can look for evidence within these layers of geological processes to better understand what's going on during the flood. For example, we find evidence for tropical storm conditions. We find evidence for earthquakes, for volcanic eruptions and tsunamis. We even find evidence for massive meteorite impacts. All of these things were happening during the flood. Again, this is more than merely just water being sloshed around over the face of the earth for a whole year. This is a worldwide catastrophic event with geological significance. Taking all of that into consideration, we have to pause and wonder, how long would it take the Earth to recover from such a worldwide cataclysm? Well, I think we can get some idea based on some more recent natural disasters and seeing how long it takes for their aftermath to finish its course. I especially want to turn our attention to earthquakes. Earthquakes today can trigger what are called aftershocks. Now, aftershocks can happen anywhere between days, weeks, months, or even years after a big earthquake. And these aftershocks themselves are earthquakes, to be clear, but they are of lower magnitude than the big earthquake that would have initiated this sequence of events. There's a really interesting series of earthquakes that happened in over a 3-month period during 1811 to 1812. It's called the New Madrid earthquakes. And this was a series of very large earthquakes, all of them magnitude 7 or greater. Now, it's been, a good 200 years since these earthquakes happened, but this area still experiences earthquakes. This whole area is called the New Madrid seismic zone. And it's thought that many of these earthquakes are actually aftershocks from that series of earthquakes that happened between 1811 and 1812. This is 200 years later, and this area is still recovering. Now, granted, these earthquakes, these aftershocks, are much smaller, and most of them can't really be felt by humans, but they're still happening. So this really emphasizes the fact that it can take a while for an area to recover from a catastrophe that happens today. So turning this back to the flood, the biggest catastrophe that's ever happened, that's not going to recover overnight. This is going to take years, decades, centuries to recover. In fact, it could be argued that many of our natural disasters today are either indirectly or directly still a result of the recovery of the flood all these years later. When we look to the early post-flood period, we also have to remember that there were other factors involved that we don't really see happening today, which would make these catastrophes far larger than anything we see in the present world. One of those factors is the rise of mountains. We know when we look at our modern mountains, they are made of rock layers, primarily those formed during the flood. We think that because the layers themselves are marine rocks. They're dominated by marine rocks. We have exceptions, but that's the general trend. And they're filled with marine fossils. Obviously, this can't happen after the mountain forms. This isn't like the flood is rising to the top of our modern mountain peaks and then dumping marine sediments and fossils on them, because the mountain itself is made of these materials. So that means the entire mountain must have been at one point either flat-lying or a low-lying area that accumulated sediment and organisms, which turned into fossils. And then later on during the flood, these areas were uplifted, forming mountains, and thus explaining why we have marine deposits and fossils thousands and thousands of feet above present sea level. Now, as a result of this, you're going to have mountains rising, especially toward the ending of the flood, but also continuing after. And this is going to result in another geologic phenomenon called mass wasting. What exactly is mass wasting? Well, mass wasting can be described as the downhill movement of rock, sediment, and other debris. Now, it's key to note here that water-saturated sediments are especially susceptible to mass wasting. And right after the flood, many of these sediments, especially the ones deposited later during the flood, they're not going to be dry and hardened into rock just yet. Many of them are still going to be wet and saturated with water. So mass wasting is going to be something that's happening a lot as the Earth is recovering from the flood. Now, mass wasting can occur in a number of different ways. There's several different types of mass wasting. You can see on the diagram I have pictured here. They can occur in the form of rockfalls, landslides, mudslides, and slumping. And as mountains continue to rise after the flood, you're going to have basins forming in between the mountains. And these basins are going to be places where sediment will collect and accumulate, piling up through these mass wasting processes. But what happens when there aren't basins and you have mass wasting occurring on a massive scale? Well, you probably would get something like this. Where there are no basins, the sediment is simply just going to accumulate in low-lying areas as these very vast sheet deposits. And we tend to see these a lot in post-flood sediments that are around the skirts of mountain ranges. For example, here I have the High Plains Aquifer. This is a sequence of sedimentary deposits that occur along the eastern flanks of the Rocky Mountains here in the United States. And I have a picture here from Badlands National Park. This is one of these deposits associated with the High Plains Aquifer. And you can see the scale of these deposits. These deposits are very thick and very widespread. Now, they're not as big as the ones we see formed during the flood, but they are occurring everywhere mountains are actively rising and sloughing off large quantities of sediment through mass wasting. So they can give the appearance of being very widespread deposits, even though the phenomenon causing them is relatively localized compared to what we see happening during the flood. Now, these sediments are absolutely full of fossil organisms, plants and animals. If you spend any amount of time at all walking around in, for example, Badlands National Park, where this photo was taken in South Dakota, you are bound to find fossils. Now, this is a national park, so please don't pick them up, but you're more than welcome to go to Badlands National Park and find some fossils. Just don't touch them. And these fossils are of animals and plants that were, many of them at least, were caught up in these natural disasters, buried and preserved. The Mississippi River embayment is probably another example of post-flood mass wasting. Now, the history of this region is really interesting from a geologic perspective. The Mississippi River embayment extends from the Gulf of Mexico into southern Illinois, as you can see from this diagram here. And it's thought that this area originally sat above an upwelling body of magma. Magma is molten rock. When it appears on the Earth's surface, we call it lava, but in this case, it never did breach the Earth's surface, so we call it magma. And from a young Earth perspective, this would be happening during the flood. So the North American continent is situated in an area above this upwelling body of magma, causing the area to bulge. However, later during the flood, when the continent is no longer sitting above this magma body, this area is going to experience cooling and it's going to sink. It's going to form a basin. It's going to deflate, if you will. And as I just discussed with basins, we all know what happens with basins. They tend to collect sediment. So you have the Mississippi and other rivers bringing all this sediment, likely through mass wasting processes, into this single area, forming this large deposit relatively quickly. But there are other types of processes aside from mass wasting that we should discuss when talking about the post-flood world. And one of them has to do with lakes. After the flood, many of these high elevation basins were filled with water and became large lakes. Evidence suggests that the Colorado Plateau here in the United States was home to a number of large lakes. One that I want to focus on in particular is called Hopi Lake, and it's located near the bottom of this map here. Now, Hopi Lake is, as you can see from the map, very large. It's estimated to have contained around 3,000 cubic miles of water. That's more than Lake Michigan. And we know that the lake was here because we find green clay deposits. Green clay deposits in particular are indicative of anoxic conditions, that is, an environment with very low oxygen. This is something you would expect to find at the bottom of a very deep lake. And we also have evidence for the shorelines of the lake. Possible shoreline markers have been identified. These are sedimentary structures that form along the edges of the lake that can kind of tell us where the boundaries of the lake were. We also find fossils that are indicative of a post-flood lake environment. We find fossils of freshwater fish and mollusks. Around the edges of the lake, we find footprints of waterfowl like geese and swans. And we even find fossils of amphibians, beavers, mastodons, saber-toothed cats, many different types of animals and plants all appear to have been living in and alongside this lake ecosystem. But if all of this was here after the flood, where did all the water from Hopi and the other lakes go? Well, turns out there's actually a grand clue just southwest of Hopi Lake. And when I say Grand Clue, I do mean grand. This is the Grand Canyon, after all. Now, there are several ideas that have been proposed to try and explain how the Grand Canyon got there, and this continues to be a matter of debate amongst geologists, both young Earth and old Earth. However, most young Earth geologists, and even an increasing number of old Earth geologists, favor an idea called the lake spillover theory. This is essentially the idea that once Hopi and the other lakes became too full, they spilled over. They spilled over a ridge called the Kaibab Upwarp. You can see on this diagram on the right here, you can kind of trace the progression of this processes from image A to F. A and B shows the filling of these lakes. Hopi Lake is on the bottom. On the top, there's another lake called Canyonlands Lake. And when the water overspilled the Kaibab Upwarp, it flowed along the path of least resistance. And as it went toward its exit point out of the Colorado Plateau, it downcut into the underlying rock, forming a very deep canyon, the Grand Canyon. It's likely that many regions that were of high elevation after the flood experienced erosion, the removal of sediment, in a similar way to this, to what we see happening at the Grand Canyon. Volcanic eruptions definitely played a very large role in the transformation of the post-flood landscape. We tend to find that the closer back in time you go to the flood, the larger and more frequent volcanic eruptions seem to be. But they're still happening today. I'm sure many of you are familiar with Mount St. Helens. Mount St. Helens erupted on May 18th, 1980, and it triggered a slew of complex geologic processes, landslides, mud flows, falling ash, all of which came together to produce 600 feet of volcanic deposits. That sounds very, very large, right? Well, not so much compared to some previous volcanic eruptions. As it turns out, Mount St. Helens, it's not actually that big compared to some of these other post-flood eruptions. In fact, Mount St. Helens is only the most recent of a long series of volcanic eruptions on the North American continent. As you can see from this image on the left, Mount St. Helens is represented by that red blob, and the other colors represent other volcanic eruptions. These represent the distribution of ash deposits from volcanic eruptions. Most of these volcanic eruptions come from what's known as the Yellowstone caldera. This is a super volcano in Yellowstone National Park, or more accurately, it is Yellowstone National Park. See, the park sits within a crater that's about 43 by 28 miles across, which is what we call the Yellowstone caldera. And you can kind of think of it as a deflated volcano, right? So after its rich volcanic history of eruptions, this area sank, forming a large crater, and now it's a national park. full of wildlife and tourists. Something to think about next time you go to Yellowstone. And as can be seen here, the amount of ash produced by this volcano also decreased over time. The Yellowstone supervolcano is the largest volcano known on the North American continent, and some of the eruptions from this volcano produced ash deposits as far away as Texas. That should give you some idea of just how massive these post-flood eruptions were. However, as time went on, the volcanic eruptions became less frequent and smaller in size and magnitude, which I'm sure many of us living in this part of the world are very happy about. But all of this volcanic activity, both during and after the flood, had very long-lasting implications, not only for life living around these volcanoes, but also the atmosphere and the environment. In fact, these volcanic eruptions influence the environment themselves. Right quick here, I want to take a quick trip back to the flood. And I want to point out that during the flood, there was a lot of undersea volcanic activity, which left the early post-flood oceans much warmer than they are today. This produced a lot of evaporation and therefore a lot of precipitation, which made the early post-flood world a very warm and wet place. However, as volcanic eruptions like the ones we just discussed continued to happen after the flood, they eventually filled the atmosphere with large amounts of volcanic ash and dust and other debris that started to block out the sun. Since the Earth's not getting all of the heat, light, and warmth that it was getting prior to this, it made the continents a lot cooler and drier. Precipitation in some regions of the world switched from rainfall to snowfall, especially in the high latitudes and mountain regions. And this snow, as it accumulated, turned to ice, which turned into glaciers that we call ice sheets. This is when the Ice Age comes into play. Now, today, you really only find ice sheets in a few places around the world: Antarctica, Greenland, and a few remote mountain regions. But after the flood, we actually have evidence that the ice sheets surged across large areas of the planet. In fact, we estimate that around 1/3 of our planet's land surface was covered in ice. Much of North America, Europe, and even Northern Asia were covered in ice sheets. And as a consequence, since a lot of the Earth's water was locked up in these ice sheets, it actually lowered sea levels. So many places that are underwater today were actually above sea level and provided places for animals, plants, and humans to live. Some of these places served as land bridges, allowing living things to cross from one landmass to another. For example, Beringia is a land bridge between Siberia and Alaska. But how do we really know this ice age happened anyway? Great question. Glad you asked. So when we look at glaciers today as they recede, they leave telltale evidence behind. And when we find that telltale evidence in places that currently don't have a glacier, we know that at some point in the past, during the Ice Age, a glacier existed there. So what is this evidence? Well, there's several, but I'm going to go through three right now. One of them is glacial moraines. Moraines are piles of loose sediment that are pushed aside as a glacier moves across a landscape. So it's going to leave that sediment behind as the glacier melts back. Even though the glacier is long gone, we can still see the moraines, showing us the extent of the glaciers. We also find glacial striations. These are scratches or etches left on a planed off surface of rock. And it was formed as the glacier moved. It picked up things like pebbles, boulders, and other rocks and debris. And all of that debris scratched the rock surface. This particular picture of glacial striations I took actually in Maine. So we know that the glaciers were much farther south than they are today. I also took the photo of this erratic boulder on the right. These are, speaking of debris that glaciers can move, They can also move giant boulders like this. If you look at the bottom left part of that photo, you see that little brown thing there? That's a bench. So that really gives you an idea of the immense scale of this erratic boulder. This thing is the size of a house, and it was put in place by a glacier. And this rock clearly, it doesn't match any of the surrounding rocks. So this enormous boulder, it's called a Daggett Rock, by the way, was moved into place many miles from its place of origin, which is incredible to think about. It's incredible to think about the power that moving ice can have. It also continued to shape our post-flood landscape as the glaciers were moving across it. For example, we have mountains and valleys that were carved by ice as it moved through the area. As you can see in the image on the top right, we also have places where the ice sheets formed dams where they would block off large lakes of water. And when the ice dam started to melt, the water would burst through, carving and cutting canyons and valleys into the landscape, like we could see in the channeled scablands on this image in the middle here. And not all glacial processes were in the mountains or as catastrophic as in the channeled scablands areas. Sometimes it was more of a gradual phenomenon in the lowlands. For example, the Great Lakes are the result of glacial movements. As the glacier moved forward and pulled back, melted away at the end of the Ice Age, it left behind a basin which filled with water, or several basins in this case, which filled with water and became lakes. And that's how our Great Lakes were formed. So as I hope I've illustrated with this talk, there were several large-scale geologic processes happening as the Earth is recovering from the flood. The world at this time is one of ceaseless change. And it's not just changing, it's also alive. We have fossils of plants, animals, and humans in post-flood rock layers showing how the Earth was being refilled after the flood amongst all of these amazing geologic processes that were happening at the same time. So in my next talk, I'm actually going to narrow in on one of these interesting animal groups that rose above the rest, both figuratively and literally, the giraffes. Giraffes actually have a very interesting history and a very interesting story to tell that I think will really help us understand how God prepared life to recolonize the Earth after the world-destroying events of Noah's flood. Thank you.